a look. I'm on page 6. And we're talking about a cone. Okay, so that's 29. Here's the cone. Okay. Gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute. I can move on before I identify what this is.
Is that dV?
Absolutely, because it's cubic feet, of course. dV over dt. The derivative of volume with respect to time. Awesome, thank you. Good. And its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. This is not a trap. So the base diameter and the height are always equal. This is not a trap. H equals D always. If it says always, then it's part of the problem. If it says when or at the instant blah, 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 that's the trap. Good. How fast is the height of the pile increasing when the pile is 10 feet high? Let's read the question one more time from the beginning. That was the problem. So gravel is being dumped from a conveyor belt, as we see it here, at 30 cubic feet per minute. At all times, the diameter equals the height. How fast is the height of the pile increasing, which means we expect a positive answer. How fast is the height of the pile increasing? And that's the trap, when the pile is 10. I have to identify the question. Once I identify the question, then I'll start the problem.
That would be dH or dt.
Of course. Exactly. The age of a dt. Again, I like us to connect the two concepts. The volume of a cylinder, and you can say, what are you talking about? It's area of the base times the height. Very easy to remember the volume of a cone. It's pi over 3 r squared h. Same thing with the area, the same thing with the volume of a cylinder, but divided by 3. So please remember these together. That will be easier. Of course, this is not required here. I put it in just to connect the two concepts. So why am I talking about the volume? Because that's what I'm given. I'm also told that the height equals the diameter. So the height, you already told me the diameter is 2 times r. So since I don't know anything about r, I will have to replace it by h over 2. So r equals h over 2. And I will plug it in. So therefore, the volume in this case is pi over 3. R squared gets replaced by this, and squared. When I square a fraction, I square the top, and I square the denominator, times h. So now this becomes a nice formula, which is pi over 12, h to the third. H to the third, pi over 12. I put a dot under the volume. I put a dot under the height. Again, why am I putting these dots? You don't have to. I think it's a good idea, so we don't forget, but you don't have to. You're not forced to. But why am I putting those dots under those two letters?
Because they are related to time.
They're functions of time. Good. So now let's differentiate. The left-hand side.
dv over dt.
Of course, that's it. Pi over 12.
Three H squared
Excellent.
times DH over DT.
That's it. So I go back. This is what they want, which means this is my variable. I will solve for it first before I put in any number or numbers. And I am on page 7. So dh over dt equals dv over dt over this whole thing, and I'll simplify. So I have pi over 4 times h squared. All this has to go to the denominator because it multiplies dh over dt. And now, when h is 10. So let's see if I have all the necessary numbers. I have this is given to us as 30, and everything has to be in feet. And this is 100 because it's 10 squared. So I have the top 30. The denominator I'll simplify and I get 25 pi. When I simplify the 4 from the denominator with the 100 from the numerator, I get 25. 25 pi. It doesn't matter. I will approximate it. Please be very careful. You put parentheses around the denominator and you get 30 divided by parentheses 25 times pi and close. Yes, that's correct. 0.382. Measurement unit. Measurement unit.
Is that feet per minute?
Yes. That's it. How do you feel about related rates, which I would not use as a title? I would say relationships between derivatives, to be honest. How do you feel about related rates? You feel a little bit better? Is there a particular problem that you would like to work on, or we move on and we come back to related rates later?
I have a question in regards to the assessment. So like with these, you were telling us like the formula for the volume of a cylinder, the volume of a cone.
So
should
the
we
volume,
expect that
yeah,
on
you
an
should.
assessment in the one that we've covered?
So you don't have you mean the next test?
Yes.
Yeah, I would like you to remember the volume of the cone and the volume of a cylinder and the volume of a sphere.
But outside of that, it wouldn't be like some.
No, no. Just also remember, it's a very good question. Very good question. At the end of the book, and I did post this.
The
You
reference
have
sheet.
yes. So it starts at the beginning. I have this. I have them from another book, and I took them off and I scanned them. So I posted all this. So you have all this information right here for the sphere, for the cylinder, and the cone, the distance formula, and so on and so forth. You're allowed to bring this in. Very good question. Anything else? Okay, I promise we'll go back to related rates after we finish this chapter with 3.10. That's the last section. 3.11 was covered a long time ago. So 3.10 deals, as I mentioned, with two different things. Differentials. That's a new word. We know derivatives, we know differentiability, we know, what else we know? Implicit differentiation, and so on and so forth. This is totally new differentials. And the other one, linear approximations. I like to start with differentials. So let's take a look. Our best friend from the very beginning is this function, f of x. And of course, our special friend, point P, with x, and of course, f of x. And yes, of course, the tangent at that point. It has to be, right? That's the tangent at that point. So tangent at P. You can say it's not a perfect tangent, should have been a little bit closer. Yes, sorry about that. I can make it a little bit closer. Okay. And of course, our second best friend, Q, which should be very, very close to P. Tiny, tiny close, very close. So in the past, this was denoted by what? What was the distance? For the difference quotient, what was the distance that we used?
Delta?
Correct. We used h, lowercase h. Right. But yes, you're right. Now, of course, we're going to use delta. Delta x or dx. So this is x plus delta x or x plus dx. They are equal. So you can say, you already told us that this was delta. Now you're calling this delta lowercase, uppercase. So they're both delta. So this delta x is exactly the same thing that we had, a minor error. So h, delta x, dx, tiny, small. Okay, they're all equal. But we're not going to use h this time. We're going to use delta x and dx. So delta x, exact change, or error if you want. Sometimes it would be an error, but it's a change in x. Then what is dx? Delta x is the exact change, but dx involves the derivative. It is the same distance, but it involves a derivative. That's why we call it differential. So this is not the exact change. It happens to be equal. But it's called the differential of x. It's the same number for this, for x. Differential of x. Good, so we established this. Of course, Q is very, very close here, but I have to zoom in because otherwise I can't explain anything. Can anyone give us the y value for Q?
Would it be f of x plus delta x, or delta y?
So one more time.
Hold on, you said the y value of q.
Yes. I am
So
plugging in
that-
this. There is no y. I am plugging in this, or I'm plugging in this.
Oh, okay.
Has nothing to do with dy. Right?
Is it f of x plus delta x?
Yes. Both of them are equal. Awesome. Great job.
So not, hold on, so not f of x plus delta x, but f of x plus delta x.
So f of x plus delta x is a height, which is f of x, adding a distance, which is delta x. So here, if I write something like this, I'm adding a y value to an x value.
So it's f of x plus delta x.
Because imagine this is 5.
Mhm.
Do I plug in f of 2 and then I add 3, or do I plug in 5? Is that clear?
Mhm.
So if this is 5, I'm going to erase it, don't write it. If this is 5, do I plug in 2 and then I say plus 3, or do I plug in 5 in the function to get this value?
You plug in 5.
Exactly. Is that clear? It's very important to understand. So if the x value is x plus delta x, that's what I have to plug in the function. If the x value is x plus dx, that's what I have to plug in the function. Is that okay, everyone? Okay, perfect. Since they are the same, I can write either f of x plus dx if I need to, or f of x plus delta x if I need to. Remember when we had here x plus h, we plugged in f x plus h. So we got f of x plus h, correct? Yes? No? Anything? Maybe?
Yes.
Perfect. Okay, so I'm on page 8. So let's continue. So we identified what dx is called. We identify what, I'm sorry, delta x is called, what dx is called. Now, I don't want to go back there. I want to just graph it one more time. For the next step. So I have the function, I have point P, I have point Q, I have the tangent, that's a tangent, I have P, I have Q, and now I want to draw a horizontal line through P and also extend and create a right triangle here. We already know that this is f of x. You already told me that this is f of x plus dx or f of x plus delta x. And now I'm going to ask what this is equal to. Can anyone identify this?
Would that be f of x plus dx minus f of x?
Brilliant. So f of x plus dx minus f of x, or f of x plus delta x minus f of x. This is what we call delta y. So now let's write what delta y means. Delta y is the exact change or error in y value triggered by delta x, which is a change or error in x. So let's stop for a moment. I need to explain this. You understand that if there is an error in the x value, it will trigger an error in the y value. So for example, if I have a disk or a washer, and if the diameter should be 5, instead is 4.9, the area of the washer or the disk will be smaller than it should be. So if I have an error in the radius, it will trigger an error in the area of the washer or disk or whatever I have. So the exact change or error in x will trigger a delta y, an exact change or error in the y value. Awesome. Finally, almost there. Now, let's look at this triangle. And don't forget, Q is very close here. This is a huge triangle. The triangle should be tiny, but I have to zoom in. So we already know that this is delta x or dx. And looking at that triangle, can anyone give us the slope of the tangent line at the point P of this function at point P? What is the slope of this tangent at P? From what we studied in this course so far, the slope of the tangent at P equals?
P prime,
You mean f prime
F prime.
of x, because this is x and this is x plus delta x, x plus dx. Awesome. That's what we studied. We studied that the rate of change or the slope of the tangent line, the instantaneous rate of change, or the slope of the tangent line at this point must be f prime of x, because it's x. If it were 3, it would have been f prime of 3. If it were 5, it would have been f prime of 5, but it's x at P, so that's why it's f prime. Awesome. Now, forget about the derivatives and look at this triangle. What will be the slope of this line based on the triangle? It will be rise over run. Stay with me. I already know that the run is dx. I'm trying to identify this. What am I missing here from what we've studied so far in this class? What could it be?
That'd be dy maybe?
So this piece is dy. This is the last thing we need to identify. Dy is the differential of y. What does it mean? The approximate change, not the exact. The approximate change or error triggered by delta x or dx in the function, in y value. And you can say, wait. If I have the exact change, why would I ever be interested in the approximated change? Who cares if I have the exact? Well, here's the answer. Most of the time, this is so much easier to determine. Now, if we're talking about human life, I don't want this. I want that. But if I want to tell my boss, hey boss, your revenue is changing approximately by this, it's okay. Or the length of a pen, the rate of change, the differential or the change or error in the length of the pen is approximately this, it's okay. It's not a life-threatening situation. And I can determine quickly this. This requires more time for any function. And what is the conclusion now? I would like you to give me a relationship between delta y and dy. So this is delta y, and this is dy. You can say, it's huge. This of your approximated value or change in the y value is huge. Look at this exact. No. Remember, Q is extremely close to P. Yes, they look humongous. This one looks like, I don't know, 2 inches, and this one looks like 5. But no, Q and P are next to each other. So what would be the relationship that you think of between the exact and the approximate? What should I put in here? And let me give you some options. Equals, greater than or equal to, less than or equal to, less than, approximate.
Which one?
Yes, I can only use one.
I say approximate.
Of course. Absolutely. This is the approximation of that. This is the exact, and this is the approximation. Awesome. We already know this. You gave it to me. So I'm going to replace the left-hand side by f of x plus dx minus f of x. I'm going to copy the symbol. And now I want anyone to solve this equation for dy. And then I will put it here.
Dy is equal to f prime of x times d of x.
That's it. We cross multiply. Thank you very much. So this is f prime of x dx. Now I will move f of x to the other side. And this is a huge, very important definition or result. Very, very important. You're going to see what and why is it and how are we using it. So first, before we apply this in different situations, I just